My name is Young, and I'm a postdoc from Lehigh University. And today I'm gonna go through my CI's tutorial. So my tutorial is on the this ICESat-2 Hackweek folder, book, tutorials, and you can see a subfolder named CIs. And I just want to note that this tutorial is updated yesterday. So I'm sorry about that because I realized that the latest CIS product, the version 6 product, has different variable name. So I just changed the code yesterday. So if you want to see the latest one, you need to pull this notebook. So if you have any problems in that, then please let us know. Yeah, so let's get started. So in this tutorial, I want to go through how to access the CI's ICESat-2 CI's product like ATL7, ATL10, and ATL20 product. And especially I use some IcePix or RTAccess libraries. So I will introduce both methods to access them. And also we're going to see what these CI's products really look like. And also from this CI's product, we will derive some CI's properties like CI's thickness, lead fraction, and flow size distribution. And finally, we are gonna make a kind of cool map of CI's freeboard maps in the Arctic and Antarctic using map product. Okay, so before we move on to the technical side, first, I'm gonna do some very brief introduction about CIs. So what is CIs? Yeah. So yeah, just ice on the sea. Yeah, very simple question. So if the seawater is frozen in the very cold weather condition, then yeah, that seawater is frozen to ice, and we call it as sea ice. And so sea ice grows in winter, so it expands and gets thicker and thicker in winter season. However, in summer season, it decreases, like thickness and extent is decreased. However, even in summer, the sea ice does not completely appear. So some of the ice survives even in summer, and we call this ice as martyr ice, which survives in summer. And I want to also highlight that sea ice is not just a flat surface. So, sea ice moves very fast. So sometimes many flows pull each other, and then it makes kind of ridges, pressure ridges, as you can see here. And also, if there is any divergent movement between sea ice flows, then it makes open spaces like open water and very thin ice, and we call that open space as lees. So sea ice surface consists of very different types of these dynamic features, such as pressure ridges, lees, some small fractures, something like that. And I just want to highlight that ICESat-2 has a very good spatial resolution to detect all of these dynamic properties of the sea ice. So we're going to see that. So the important part is that how ICESat-2 measures these sea ice properties, especially sea ice thickness. Basically, the physical metrics ICESat-2 directly measure is sea ice freeboard, which means the height of the sea ice surface above the sea surface. So this is the sea ice freeboard, which ICESat-2 directly measures. So so basically ICESat-2 CS product just subtract this local sea surface height from sea ice surface to calculate this freeboard. So then it is pretty critical to separate the height measurement from this sea ice surface from this water surface. So this is the critical part of the ICESat-2 freeboard product to calculate this this just freeboard. So basically, there are three products in CS products. So first one is ATL07, which measures the CS height. ATL10 is CS freeboard, and from this ATL10 product, we can get the monthly gridded product, which is called ATL20. So ATL7 product basically calculates the height of the sea ice above the reference ellipsoid, and as you know, this reference ellipsoid is WJS84. So ATL7 product just measures this surface height relative to a reference ellipsoid, and then ATL10 products calculates the surface height between this sea ice surface and sea reference surface. So basically, it measures this freeboard. And also ATL07 product provides some kind of surface classification. So it determines this signal is from sea ice or this signal is from seawater, so something like that. So based on that ATL07 surface classification, ATL10 product distinguish these two different type of surfaces and calculates freeboard. And there are two types of leads actually ICESat-2 can detect. So if you think about the open water spaces or very thin ice surfaces, it can have two different either reflectance types. So basically the key properties ICESat-2 CS product measures is called photon rate, which means the number of photons returned to the satellite per shot. So if the photon rate if the photon rate is high, then that means more and more photons come back to satellite for that surface. But if that value is low, then less number of photons return to the satellite. So basically, leads can have either higher photon rate or low photon rate. So if you think about so open water space is very smooth. So it's like it can be like a mirror. So it can be very specular. In that case, more and more, many number of photons can return to the satellite. In that case, lead have very high photon rate values. However, at the same time, as you know, water has very low reflectance. So in that case, most of the photons are observed by open water or something. So the number of photons returned to the satellite is not that much. So in that case, that lead have very low photon rate values. So these CIS products detects two types of leads. One is specular leads, which have very high photon rate values, and the other one is dark lead, which means it has very low photon rate. So this is a cool figure from Alec Perry's paper. So this is some example of the ATL07 product. So this is the coincident optical images, and you can see these leads, some types of leads have very high photon rate values, and these leads are detected successfully as the specular leads. However, here's the issue. So in this area, you can see this red line means it's detected as dark lead, and in this some cloud area, actually this cloud blocks the photons. So even though there are no real leads, but this cloudy area is misclassified as dark lead because the number of photons returned to the satellite is not that much. So in this kind of cloudy area, there is an issue like dark lead misclassification issue. So that's why the latest CIS freeboard product only uses specular leads for the freeboard calculation. So that is the basic of the basic knowledge about ICESat-2 CIS products. And before we move on to the technical part, do you have any questions or comments about CIS product? Yeah. Yeah. I don't think we have any questions. So yeah, let's move on to the technical part. So in this tutorial, I will introduce some ways to access these CI's products. And actually, we already cover all of this stuff in previous tutorials. So first way is to use ICEPix. So you can open this first notebook and just run these cells. So import this ICEPix, and I will make a ICEPix query. And in this tutorial, I set up the spatial extent as a Ross Sea area in the Southern Ocean, and also this time range. And in this tutorial, I'm gonna see two tracks. One is from September, and the other one is from November. So let's first take a look at the September one. So make a ICEPix query like this, and you can visualize the spatial extent like this. So yeah, the spatial extent I set up is this area in the Ross Sea. And you can get the information, summary information like this. And using the ICEPix, we can either remotely access to this data or just download this data to your local machine. So you can choose either one. So first, if you prefer to use remotely access through the cloud, then you can use this one with your own Earth access information. Then we can get the link for that area. So there is one track for this region and this date. And but if you also prefer to use some locally downloaded files, then you can run all of this code. But in this tutorial, I'll just go through the remotely accessed data. And the other way to access the CI's product is to use Earth access. So you can also go through all of this part. And here, once you get the Earth access query, then so here in the Earth access collection query, I put the keyword of ATL10. Then you can see all of the products that has keyword ATL10. So there's ATL10 and ATL20 and ATL21 product. And all of this product has its own concept ID. So in this tutorial, I just want to see if you want to see the ATL10 product, then you can just put this concept ID here. So if you want to see some other products like ATL7, ATL10, and ATL20, then you can use different concept ID here. So by using this code, you can also get the Earth access query. And there's one granular as well. And you can visualize it. So yeah, this is a ATL10 granular. We want to see it. So yeah, there's one file. So this is how to access the CI's product. And yeah, I believe we already covered all of this stuff like ICEPix and Earth access before. So I believe you're so familiar with it. So let's do some practice with the real track product. So first, let's import these libraries here. And actually, I also locally downloaded these files in this folder. So you can either read this locally downloaded file in this shared folder, or you can access the cloud file. So these two different parts same has an output of file name, and we're going to use this file name to remotely or locally access to the data. So, but yeah, as I said, I will do the cloud access. So file name is here. And before we read this specific file, I just want to see the orbit orientation, because for the CICE product, this orbit orientation is pretty important because it determines which is strong beam and which is weak beam. And as you remember, at the very first day, Nathan introduced about the CICE products a little bit, and actually the CICE product, the ATL-07 product is generated by aggregating 150 photons. So it's more like it's not a fixed distance approach, so it's more like fixed photon approach. So for the strong beam and weak beam, so strong beam has more strength. Yeah, strong beam is 4 times stronger than the weak beam. So the number of photons returning to the satellite is more for these strong beams. So this means that it takes pretty shorter distance to collect these 150 photons, which means strong beams always have the shorter distance or better spatial resolution in measuring this surface height compared to the weak beams. So in this tutorial, I will only use the strong beams. So if the orbit orientation is forward direction, then as you can see here, the right beam is the strong beam. But if the orbit orientation is backward, then left beam is strong beam. So first, I would just want to check if this granular data is forward or backward. So this value 1 means that this phi has forward orbit, which means that the right beam is the strong beam. So we're going to use only this right beam in this tutorial. And I made this just very simple function to read these ATL-10 files. So from this orbit information, I only select the strong beams. And then I will read the latitude, longitude, segment distance, like along track distance, and segment length, freeboard and surface type. And here I just want to filter out some invalid freeboard values, which has freeboard is greater than 100 meters. So I'll just the freeboard is greater than 100 meters, then I will put null value for that height segment. So then if you run this file, then you can get the kind of list which has 3 elements for 3 strong beams. So in this part, we're going to draw a freeboard profile. So in this part, I will select the first strong beam. And if you draw, then it looks like this. And here I just add some mask, like which part is CIs and which parts are leads, something like that. So here, these blue dots are normal CIs, which is not lead. And the red one is a specular lead, and black one is dark lead. And actually here you can see some of the abnormal values, like lead should be very thin ice or open water, but this part has kind of higher freeboard values, which does not make sense. And this is because, as I said, there is the kind of dark lead misclassification issues. So near the clouds, some of the dark leads are not correctly detected by this algorithm. So, and also, I also want to highlight, I just want to note that ATL-07 and ATL-10 products are more focused on the accurate estimation of freeboard values. I mean, not for the lead fraction or full size distribution, something like that, because, if some of the non-lead part is detected as the least, then it makes a lot of uncertainties or errors in freeboard estimation. So this ATL-10 product only detects the least that we can 100% sure this is really least. So this algorithm is not designed to detect all of the leads. So some of the leads can be missing by this algorithm. So you can see there are very few number of specular leads here, and only the specular leads are used for the freeboard estimation. And also here, if you zoom in some part, like for example, I will zoom in to this area, then as I said, the CI surface is not flat, so it is very dynamic, like up and down. So you can here you can see the CI surface is changes pretty much. So you can check these patterns. And also I calculate some kind of lead fraction, but as I said, ICESat-2 is not this CCS product is not designed for the accurate lead fraction. So instead of just using the specular lead and dark lead fractions, I add these freeboard values as another indicator of leads. So if the freeboard value is so low, then we can say that that part is leads. So for example, in this part, I define the 0.1 meter as the threshold. So if we consider this part like freeboard is less than 0.1 as the least, then you can see the like 6.7% of this track is least. But as you see here, I don't know. Oh yeah. Sorry. Yeah, so you can just go over of this part. Yeah, and here you can draw some histograms of this track for 3 strong beams. And if you see this histogram, you can see the histogram of the freeboard, and you can see there is a kind of this is look like bimodal distribution. Like first peak in here, and the second peak is here. So you can just consider this first peak as the very thin ice or lead, and the second peak or the other part represent just normal sea ice surface. And so here I just used the track from September, but in this part I encourage you to use another November track, and I already downloaded it in this shared folder, so you can do it by yourself, like read the November data and what are they different from the September track, because in the Southern Ocean, September is the end of the winter, so sea ice extent is maximum and sea ice is the thickest. However, it starts to melt in November, so there should be some different patterns. So you already have the file name, so maybe you can just copy and paste all of this code. Yeah, so this is from the November data. So yeah, this is from September and this is from November. And it is obvious that in November data, more leads are detected. So yeah, more specular leads are detected. And this is because CI starts to melt in this November season. So there should be more leads. And yeah, so like this, you can also try some other tracks. So right now, if you change these numbers, like zero means I just extract the first strong beam, but you can also see the some other beams, like one means center beam and two means yeah, the third beam, third strong beam. So yeah, you can compare these tracks and what they look like. And also you can draw a histogram for this November data. And absolutely you can see the freeboard values decreased compared to the September. So there should be obvious melting or formation of more leads in this November season. So far, do you have any questions or comments? Yeah. Okay, great. Then let's move on to the gridded product. So here we're gonna see some ATL20 product. And before, for the single track data, I use IcePix query, but for this gridded product, I want to show you how to use the RThoccess query. So in this part, I just use RThoccess to access this data. And actually, this gridded product is monthly product. So this means each month has one product. And also this gridded product covers the entire Arctic or the Antarctic. So here, if you, for this temporal query, if you put any specific date or month, then you can get only one single data for that month. And also for this bounding box, if you put any region in the Arctic or Antarctic, then you can get the file for the entire Arctic or the entire Southern Ocean because it covers the entire area. So yeah, there's one gridded 20 gridded files, one gridded file for September. And we're gonna read this one. And it has latitude, longitude information, and this gridded product has 25-kilometer grid cell, which is projected to NSIDC sea ice polar stratigraphic south projection style. So here, by using this one, you can draw a cool map of monthly sea ice freeboard grid like this. So right now I tried the September data, but you can also try some other month as well. And also for the Arctic, you can try it. And for the Arctic data, I want to use March data. So the Arctic data freeboard looks like this. And for the next part, you can try your own like map for another month. So for example, here generally March has the kind of very large sea ice extent and thick sea ice. However, if you want to see some other seasons like melting season, then you can just change this month. So for example, I will change it to August. Then August map looks like this. So you can see a much smaller sea ice extent and also much thinner sea ice thickness like this. So that is how to use this gridded product. So if you want to see a kind of patterns, like special patterns or temporal patterns of sea ice thickness or sea ice freeboard in the Arctic and the Antarctic, then this gridded product is very useful for the general patterns or something like that. So I just put some helpful references for the sea ice product, so you can read these papers if you want. And for the second part, actually, this part I add this part as a kind of optional one, but I have some time, like 5 or 10 minutes, so I will briefly go over this part. And this notebook is more about validation of this sea ice product using Sentinel-2 optical images. And here I just use Google Earth Engine to find some coincident Sentinel-2 images, which is pretty similar with the tutorial in the yesterday. So by using Google Earth Engine, I will make a Google Earth Engine query to find Sentinel-2 images, which has the exact same location and time with the ICESat-2 data. So here I just make a ATL 10 track and make it as a Google Earth Engine feature collection. And then I also get the time of the ATL 10 track. And then I'll find the Sentinel-2 images, which is the same date and same spatial coverage. And there are 3 images available for that ICESat-2 track. And this is the ID of these images in the Google Earth Engine. And by using this part, you can draw the map of this track and Sentinel-2 images, and it looks like this. So this is the ICESat-2 ATL 10 track, and this is the Sentinel-2 images. And actually, it is pretty challenging or difficult to find the overlapped sea ice images, optical images, because sea ice moves very fast. So even in some hours, the sea ice distribution changes very much. So it is pretty challenging to find exactly same location and within a few hours of time difference between ICESat-2 and Sentinel-2 tracks. And also there should be no clouds. And these optical images are only available in summer season. So in the polar winter, there's no sun, so there's no optical images available in this area. So there's many limitations in getting this overlapped image for, especially for the sea ice. But yeah, you can find some a very few number of overlapped images. And actually, I already downloaded this image, overlapped Sentinel-2 image in the shared folder. And so I will read this image using Rasterio and visualize it and compare this image with the ICESat-2 track data like this. So first one, I just visualize the surface type, which is determined by the ITL 07 product. And as I said, so if I zoom in, for example, this area, . And you can see, so here this green dot means it's a sea ice, and this brown one is the leads detected by the 8807 product, and you can see the general pattern looks pretty good. So there should be some leads like this open water, and also here, but some other area of the sea ice covers. And also in terms of the freeboard values, if I zoom into the same area, then you can find so some thin ice or gray ice has very low freeboard values, as you can see here. So that is kind of overlapped with the this thin ice area with the low freeboard. So from this result, you can at least say ICESat-2 has good performance in detecting leads by using this freeboard or its surface classification algorithm. And finally, I want to compare some flow statistics, which is derived from ICESat-2 and Sentinel-2. So here, this is just a histogram of the pixel value from Sentinel-2 images. And the reason why I did this is to kind of create a binary image to get the flow statistics. So here, I believe this part should be some sea ice, and this part should be some thin ice or open water. So I just put the 9,000 as the threshold to determine sea ice and lease area. So by using this threshold value, I made this kind of binary images to get the sea ice flows and non-sea ice part like lease. And from this binary image, I can calculate this distribution of sea ice flows, and also from the ICESat-2 along this track. So this code is just for the flow size distribution using the lead mask. So if you run off this part, so here this is the flow size distribution along this ICESat-2 track. And this blue one is from ATL10 freeboard threshold for the lead detection. And this orange one is from Sentinel-2 pixel value threshold values. So here you can see the general pattern of this flow size distribution looks pretty good with ATL10 and Sentinel-2. So, and this is the flow size distribution, and this is the lead length distribution. And these two, from these two histogram, you can see they look pretty similar. So at least we can say ICESat-2 has good performance in measuring freeboard values or finding some leads based on these freeboard values. So yeah, that's pretty much for my sea ice tutorial. Do you guys have any questions or comments? Yeah. Yeah, we're good to go.
Let's thank you
Thank you.
for a great tutorial.